Good evening. It's my name is Thray Rahlan. I'm a committee member of the Institution of Mechanical Engineers Aerospace Northwest, and I would like to first of all invite you to this. Wish you a warm welcome. Depending on which part of the world you are, it's a good afternoon or good evening or good morning, as the case may be. This is yet another lecture that this particular committee has organized, and just one or two domestic issues. First of all your microphones and cameras have been disconnected. Please submit your questions using the attendee questions facility. And the other thing is this webinar is being recorded. And so the web link will be sent to all attendees for anyone to view at a later date. At this point in time, I would like to introduce our speaker today. It is Manuel Donald-Lopez. He's a chartered engineer and a member of the Institution of Mechanical Engineers. He joined BAE Systems at the start of 2002 on the graduate development program. And then he went on placements on Eurofighter Typhoon, the Nimrod MRA-4, and the Joint Strike Fighter. He remained on the Joint Strike Fighter program, working on field systems development, now known as F-35 Lightning II. He developed field control systems for pre-production conventional takeoff and landing CTOL prototype. First flight was in 2006. And then the other model, the short takeoff and vertical landing variant, the first flight was in 2008. And then the production conventional takeoff and landing variant, the first flight was in 2009. And the carrier variant, first flight was in 2010, all of which have different fuel systems. He led the continuous development of fuel control systems through the F-35 development and demonstration phase. That's the flight test phase, and currently provides F-35 fuel system support to worldwide fleet and work on development of system improvements. That is aerial refuel tanker integration, external fuel tanks, and use of synthetic fuels. And at this point, I'd like to hand over to Manuel.
Thank you very much. All right, so I'll just share my screen so you can see the presentation. All right, so this is going to be hopefully an informative talk about fuel systems, and well, the content of tonight's presentation is going to cover fuel system functions, fuel system interfaces, go through some fuel types, fuel tanks, and then we'll walk through each of the subsystems in turn. So first of all, I'd like to say thanks for taking the time to watch the presentation. I hope you get something out of it, and at the end, have a better understanding of the complexities of aircraft fuel systems. Thank you very much to Sarah for the introductions. So we've kind of covered my background, so we'll crack on and start talking about fuel systems. So the first slide we're going to look at is some typical fuel system functions. We're going to do this by building up a simple fuel system schematic. So we'll start off with an engine. So the first function is fuel storage. So we need somewhere to put the fuel. So in this case, we have a fuselage tank and 2 wing tanks. The next function is to provide fuel to the engine. So we have a boost pump in the fuselage tank and a tube to the engine. Then we need to provide fuel to the collector tank. So now this tank's got a boost pump in it. It's known as the collector tank. So we now have transfer pumps in the wing tanks, which can pump fuel into the collector tank. We need a way to fill the tanks up and defuel the tanks. So we have a refuel system with shut-off valves into each tank, and in this case, there's a ground refuel connection point and an aerial refuel connection point. We need a way of managing pressure within the tanks. So there's a vent system, which is a tube with openings into each tank, and a control valve to allow the system to depressurize or stay pressurized. Some aircraft need to jettison fuel to maintain landing weights, so we have a shut-off valve which links to the transfer lines to allow us to pump fuel from some tanks overboard. Most modern aircraft use fuel as a heat sink, so there's a heat exchanger on the aircraft, and we can pump fuel through the heat exchanger and provide thermal management for other systems. We need a way of measuring the fuel in the tanks, so we have some gauge probes in the tanks and some way of displaying the fuel contents to the pilots. Quite a few aircraft now have explosion suppression. So in this case, there's an onboard gas generation system which takes bleed air from the engine, passes it through a air separation module, and then pumps nitrogen into the fuel tanks. This also provides a way of pressurizing the fuel tanks. There needs to be a way of controlling and monitoring all the equipment on board the aircraft as well. So there's all the wiring and the avionics computers to control the fuel system. So now we're going to look at how the fuel system interfaces with the other parts of the aircraft. So I'll start with airframe structures and go around clockwise. So the airframe houses all the fuel tanks and all the pipework, and there's a lot of work to route and mount all the equipment. So there's a lot of integration between the airframe team and the fuel team as the design evolves. The fuel tanks need to be stressed to withstand positive pressures and negative pressures generated during system operation. The propulsion system requires fuel delivery at the correct rate and pressure, and may also use fuel system sensor information for temperature and density. The fuel system usually has quite a lot of electric equipment, so fuel pumps and sensors and valves. So the electrical power system provides power to all those, and we need to coordinate with the electrical power system for load shedding if there's a failure to make sure that fuel is still delivered to the engine. The flight control system is another quite large interface with the fuel system because we provide CEng management for the aircraft. We need to make sure the CEng position remains within acceptable limits, and the flight control system will also use weight information. Thermal management, as I mentioned, we usually provide cooling to other aircraft systems by heat exchangers. So there will be flow rate requirements for the heat exchangers. For cockpit displays and controls, there's usually a fuel page displaying the tank weights and control buttons for various functions of the fuel system. Fire protection system, we tend to have an interface to shut off fuel to the engines in the event of fire. For hydraulics and actuation systems, this is mainly used for aerial refueling, so there'll be doors to open or probes to extend, which require hydraulics, and also latches to latch in some of the refuel equipment. So the aircraft wiring, there's another large interface where we need to ensure all the equipment is connected to the appropriate computers and wired up so it's redundant in case of failures. The landing gear system usually provides information of when the gear is lowered so we can depressurize the fuel system for safety reasons. For health management systems, there'll be hundreds of fault codes related to fuel systems, so we have an interface there to make sure we raise the correct fault codes when required. For the avionics system, again, we have usually a field computer with thousands of lines of code for controlling all the equipment. Mass properties require knowledge of the fuel tanks because they are quite a large contributor to the aircraft total weight. So they need to know the CG position and the tank quantities. External tanks may be fitted to the aircraft. These have interfaces to provide fuel inside the aircraft, and also we need to pressurize the external tanks or provide a pump to pump the fuel out. For tanker aircraft, there's interfaces to connect to the tanker and make sure the receiver aircraft interfaces are strong enough to withstand the loads seen during aerial refueling. And lastly, ground equipment needs to be able to connect to refueling equipment or test equipment in a way that is safe and ergonomic. So moving on. So this next slide shows some fuel types. So there's two main types of fuels: aviation gasoline, which is used for piston engine aircraft, and turbine fuel used for jet engine aircraft. The aviation gasoline is kind of categorized as an octane rating, and there's a few equivalents in the US and the UK. The main one used today is Avgas 100 LL, which stands for low lead. The aviation gasolines tend to be coloured as well to aid in identification, and that's to help prevent misfueling of piston engine aircraft with turbine fuel, which can cause significant damage to piston engines. The turbine fuel, as you can see, there's quite a few different types. There tends to be a fairly common type between different countries. So the US Civil and US military have some equivalent types, and then the specifications that govern these types of fuel will determine things like flash point and freezing point. And that's why the Russian fuels tend to be at the lower freezing point because the country's colder. You can see that China tend to match both Western and Russian fuel types. And then the NATO coding is used to allow NATO operations to have a common fuel source. So if you fly on a civil jet, you're likely to be using JSA1, which is governed by the most stringent requirements of the UK DEFSTAN 9191 and the ASTM D1655, which is the US civil specification. So this next slide goes through some synthetic fuel types. So this shows the 7 currently approved production pathways for synthetic fuels. The top row is the short name, and the second row is the long name, which kind of gives a little bit more information about the process used to produce the fuel. But the end product is effectively just kerosene. The third row is a blend limit, so the synthetic fuel can be blended with a conventional fuel. So for example, Jet A1 by up to the amount shown in there. And then the next row shows what the fuel could be made from. So when you hear the term biofuel or sustainable aviation fuel, this is what it's talking about. as you can see, in some cases the fuel may be made from something that wouldn't be particularly environmentally friendly, for example coal. So in that case there wouldn't really be any benefit for the environment, because you'd basically be burning coal instead of kerosene, which is effectively the same thing. The environmental benefit can come from using plants as the feedstock. So for example, if you do the heifer SPK process and use bio-oils for feedstock, you can obtain an environmental benefit by making sure the CO2 absorbed during production is equivalent to the CO2 burned as the aircraft flies around. But there are some significant challenges in achieving an environmental benefit, in that the blend limit means that the CO2 absorbed needs to be effectively twice as much as the CO2 the aircraft burns. And if we use something like the oil-rich plant camelina, it would require 1 million square kilometers to produce 50% of the current jet fuel requirements. To put that in perspective, the current worldwide corn production covers 800,000 square kilometers. So in other words, that's not really a feasible thing to achieve. A slightly more feasible opportunity is to use algae, which would require 34,000 square kilometers to provide the 50% of the fuel. That's still equivalent to 56% of the UK's arable land. And the other issue is that the cost of producing synthetic fuels can be up to 10 times as much as crude oil-based fuels. So there are some significant challenges to overcome to achieve a net carbon zero aviation. From a fuel system perspective, the important properties that can be altered when using synthetic fuels is density and dielectric strength, both of these which can impact fuel gauging. Synthetic fuels are less dense than crude oil, and that's one of the reasons for the blend limit, because when you have blended the fuels together, you still have to meet the original specification of the fuel, and density is a spec requirement. The other impact that can occur with synthetic fuels is seal shrinkage. So the synthetic fuels have a reduced aromatic content, which can result in seal shrinkage. So I'm just going to look at some fuel tank types. So typically there's 4 types of fuel tanks you can use. You can have elastomeric removable tanks, which can be hung inside bays in the airframe, and these can be self-sealing to provide additional survivability. You can use rigid removable tanks, which could be made of light alloy or fiberglass. Again, these are placed inside fuselage bays or wing bays. The more common type on military aircraft is integral tanks, where the tank is part of the airframe with wet bays created with sealant. And then final tank type is external tanks, which are temporary fit to extend the range for an aircraft. You don't typically see these on civil aircraft, but some general aviation aircraft do have them, but it's more common in military aircraft. So now we go to fuel tank layouts. So general aviation is an example on the left, which is the Cessna 150. So it's got a couple of tanks in the wings. In this case, the capacity is about 98 litres. The airliner shown on the right is a typical airliner layout with a fuel in the wings and a centre tank. So in this case, there's 138,000 litres. And then This next slide shows an example of a military aircraft. In this case, it's an F-35 pre-production prototype. And the difference you can see here is the fuel it's stuffed in wherever it can fit. So you tend to have tanks that are quite odd shapes and quite difficult to gauge. So the capacities of this aircraft are about 10,000 litres for the F-35A variant or CTOL, 7,500 litres for the STOVL variant, and about 11,000 litres for the carrier variant. So I'm going to move on to some of the subsystems. So engine feed for general aviation can be quite simple. If you have a high wing monoplane with a piston engine and a carburetor, then you can just use gravity to feed the engine. This does limit the aircraft to level flight, as the engine will cut out if the aircraft is inverted. If you have a low wing monoplane or engines with fuel injection, then you do need a boost pump to provide sufficient fuel to the engine. And if that's a dual-ended boost pump, then you can achieve inverted flight, because then you can still pump fuel to the aircraft. This slide shows an example of a civil aircraft feed system. So the engine feed tube is shown in black, and there are two main pumps for each side with a cross-feed valve that can separate the two sides. So during normal operation, the two main pumps would run and provide fuel to each engine. If there was an emergency, then it would be possible to open the cross-feed valve and feed both engines with one pump. If the pumps in the collector tanks fail, then there is a standby pump in the inner tank to continue to provide fuel to the engines. And then you can see there's an LP valve, so you can shut off fuel to the engines if there's an engine fire. So for military aviation, the engine feed system has to provide fuel to the engine at a sufficient pressure, and that engine fuel demand increases dramatically if the afterburner is used. The feed system also usually provides cooling to other systems, which can include avionics, hydraulics, engine oil, and engine FADEX, and electrical generators. And we usually provide an engine fuel shut-off capability. You can see an example of a dual-ended boost pump, which is used on the F-35. This shows an example of a military aircraft engine feed system, which is typical for a twin-engined aircraft. So what we tend to do is have a forward group and an aft group of tanks, and then each group will feed a different engine. So this example is an F-111. So the forward group provides fuel to the left engine normally, and the aft group provides fuel to the right engine. But it's possible to use a cross-feed valve and provide fuel to either engine using either tank group. But normally the pilot would leave it in the auto position and let the aircraft sort itself out. In auto, there is also CG control, because you can transfer aft fuel to the forward group using the aft exfil valve shown here. The engine feed system also provides the defuel capability by pumping fuel out to the ground defuel receptacle. And there is suction feed available in this aircraft from the reservoir tanks to both engines. And you can see the low pressure valves, which can also be used to shut off fuel to the engine. So this slide shows an example of a transfer system. So we don't tend to need a transfer system on a general aviation aircraft because the tank layout is pretty simple. On civil aircraft, you've got the fuel in the wings, which needs to transfer to the collector tanks. So this particular example is an A330. So the inner tanks burn down to 4,000 kilograms, and then the trim tank can transfer into the inner tanks, and then the outer tanks transfer to the inner tanks by gravity. This particular aircraft has CG control by using a trim tank in the tail. So the top diagram shows the transfer of fuel from the engine feed system to the aft trim tank, and the lower diagram shows transfer from the trim tank back into the inner tanks, which is achieved by using a pump in the trim tank and a valve. So for military aircraft, tends to be quite a lot more fuel tanks and also tighter CG limits. So longitudinal CG is typically allowed to move 20 to 30 centimeters, and lateral CG is typically allowed to move 5 to 10 centimeters. And the function of the transfer system is to move fuel to the feed tanks whilst controlling the CG. So we tend to use several ways of doing this. You could use electrical fuel pumps or jet pumps or siphons or pressurized air or gravity. And there's usually control valves used as well to sequence transfer. So diagrams shown here show some pumps. The middle one is a jet pump. So the motor flow will be provided by the transfer pumps, all the boost pumps. And then it goes through a venturi which creates suction, and then it allows you to pump fuel from one tank to another tank. Siphons and pressurized air are effectively the same kind of thing, where you have a high pressure in one tank and a lower pressure in the receiving tank, and then the fuel will flow between the two. So this chart shows the kind of analysis that you do to determine if your CG is going to be acceptable. So it kind of shows a theoretical example with 11 tanks. So this would be a twin engine aircraft. And the idea is you have a fuel distribution plot, and on the right hand side, that's when the aircraft's full, and then as it goes towards the zero, that's when all the tanks are empty. And then by using this distribution plot, you can calculate the CG of the aircraft, and that's the two plots shown at the bottom. And then you'd be given some limits by a flight controls team, and they would be the CG requirements. And then as the tanks burn, you can calculate whether you're going to meet the requirements or not. And the bulges on the plots show fuel pitch or fuel roll as the tank's empty. So as the tank's half full, the fuel slosh in the tank is most extreme, and that will give you a worse CG position. So in this case, there's been a slight exceedance of a 50 alpha limit. So what we would do in that case is adjust the burn sequence a bit and move the overall CG forward a little bit for that point to stay within that limit. The lateral CG is okay for this aircraft as it is, but that's mainly because the tanks are ideal and symmetrical, whereas as we saw with the F-35, that's really the case because there's lots of other systems competing for space on the aircraft. So you tend to have asymmetric tanks, which would lead to a slightly different CG position left and right. So moving on to refuel and defuel. For general aviation, typically refuel via filler caps for each tank. There's not necessarily a specific defuel capability, but fuel can be sucked out by fuel trucks. You could also drain the tanks using the pencil drains, but that might take a while. Civil aviation, there's a single or dual point refuel, which fills all the tanks at the same time. Dual point refuel is used to reduce the fuel time. Fuel is automatically shut off at preset contents or when the aircraft's full, and you can control the refuel from a ground panel or within the cockpit. Defuel is usually achieved using the boost pumps to pump the fuel off board, and electrical power is required for refuel and defuel operations. So for military aircraft, it's similar to civil, but unlikely to have dual point refuel. Refuel and defuel can usually be achieved without power, depending on the operating base. For aerial refueling, that's typically military so far. So there's two ways of doing it: the boom and receptacle method and the probe and drogue method. Boom and receptacle, the tanker flies a boom into the receiver receptacle, and then there's hydraulic latches inside the receptacle to grab onto the boom. Once latched, the receiver aircraft sends a signal up to the tanker via the boom, and fuel flow can then start. So the first automatic boom refueling was achieved in April 2020 by the Airbus multi-role tank transport. The other method is a probe and drogue, where the receiver flies the probe into a drogue trail behind the tanker. The tanker pod then has to reel in the hose on contact to remove any slack. We'll see what happens when it doesn't work in a minute. So fuel flow starts mechanically when probe is engaged. A UAV automatically refueled for the first time in 2007, and the first tanking with the UAV tanker occurred this year. So coupling two systems together in flight is quite risky, as we'll see in the following videos. So this first video shows a E3 Sentry receiving fuel from the tanker. Now the tanker can see where it's supposed to be positioned by looking at the lights on the bottom of the tanker. I mean the receiver, sorry. And then in this case, he sees the boom envelope and then almost crashes into the tanker. So this video shows a typical probe and drogue mishap where initially the pilot misses the drogue and then repositions and tries again. But on the second attempt, sets up a wave in the hose. That's where the probe, the drogue should have been retracted as the probe contacted, but in this case it doesn't look like it did. And that results in a wave which then travels up to the tanker and then back down to the aircraft and usually snaps off something. In this case, the drogue got snapped off, so then you have fuel spraying out everywhere. So moving on to pressurization and vent systems. So this function is similar on all aircraft types. We pressurize fuel tanks to prevent boiling at altitude, which is mainly military. We pressurize fuel tanks to enable fuel transfer. We allow air to vent into the tanks during descents. We allow air to vent out of the tanks during climbs. And we also allow air to vent out tanks during refuel. So the picture shows an example of what can happen if you do refuel with a blocked vent, in which case the tanks overpressurize and exceed structural limits, which then results in the aircraft getting catastrophically damaged. So fuel quantity indicating systems in general aviation, it's most likely to be a float type gauging system where the float moves and resistance changes, and then a gauge in the cockpit moves in proportion to the resistance change. For civil aviation, the majority of aircraft use a capacitance-based system. Boeing 777 uses ultrasonic systems, but Boeing hasn't used this on the 787. Both methods use number of probes to determine the height of fuel in a tank. So capacitance systems use changes in capacitance as probes covered in fuel, and ultrasonics measure speed return of a pulse from the fuel surface. In military aircraft, the majority of aircraft use capacitance-based systems. The Lockheed F-22 did try ultrasonics, but this has not been adopted going forward by Lockheed. So this chart shows a basic process for a gauging system. So on the input plane, we have probe capacitance. So as the probe gets immersed in fuel, the dielectric changes on the probe. Because the fuel isn't conductive either. So as the probe is fully covered in fuel, the dielectric changes to a higher value. And then a compensator or a K-cell is usually placed in the tanks to work out the dielectric strength of the fuel. You measure temperature so you can calculate density. And then you need to know the aircraft orientation and accelerations. So in processing one, the first thing to do is to combine the probe capacitance and the compensator to work out the probe coverage. And then you can use the compensator and the temperature to calculate the density. The aircraft orientation and accelerations is used to calculate a fuel angle. And then the fuel angle with the probe coverage is used to calculate a fuel volume in a tank. And then the volume in the tank times per density gives you the fuel weight displayed to the part. So fuel jettison, or dump as it's called in America, is not usually used on general aviation, as the max landing and takeoff weights are typically the same. It is provided on airliners because typically the max landing weight is much lower than max takeoff weight. So for example, for an Airbus A330, max takeoff weight is 242 tons and the max landing weight is 187 tons. So in an emergency, you have to jettison about 50 tons of fuel in 10 minutes. For military aviation, it is provided for some aircraft for the same reason as civil aircraft, but not provided on all land-based aircraft. It is essential on carrier-based aircraft though. And usually the time to jettison is compressed compared to civil aircraft to about 6 to 7 minutes, but the amount of fuel will be a lot less. So explosion suppression. This is not typically fitted to general aviation aircraft, but on civil aviation, it's been driven by TWA Flight 800, which was a Boeing 707 747 flight from JFK in New York to Rome. That aircraft exploded in midair 12 minutes after takeoff and was caused by ignition of fuel vapors in the center tank due to a wiring short circuit. So on the 21st of July 2008, the FAA required operators and manufacturers to incorporate what we call flammability reduction means, or ignition mitigation means, on fuel tanks which have flammability exposures to which exceed certain levels. So these amendments affect all new aircraft types, new aircraft in production and in service, and then aircraft produced after January 1st, 1992. So on military aircraft, we install these explosion reduction means to usually protect against ballistic damage. On F-35, we also use a system to protect against lightning strike. So there's a few ways of doing it. The first way is to use explosive suppressant foam. So this provides a simple system for approximately 3% reduction in fuel. It's primarily used on military aircraft. It does prevent explosion, but it doesn't actually prevent the ignition. Another way of doing it is stored gas inerting. So this is where you have a compressed gas canister stored in the aircraft somewhere, and you can press a button in the cockpit to provide short-term fuel inerting. So this is usually used primarily on military aircraft to provide ballistic threat protection in enemy airspace. And then the final method is to use an onboard inert gas generation system, or OBIGS. So this provides inert gas for the full duration of the flight and usually uses a permeable membrane technology. There's another way of doing it called pressure swing absorption, which has been used on B-22, AH-64 and C-17, but is not widely adopted. So this diagram shows an example of an air separation module or permeable membrane OBIG system. And the picture is an airliner multi-ASM pallet. And then the flow diagram at the top shows the various components which are labeled on the photo as well. So first thing is to get some bleed air from the engines. This then goes through a pressure regulation valve, and then which is labeled number 1, and then into a filter and water separator, which provides conditioned air. That then passes into the air separation module itself, which are the 3 big canisters shown in the photo. The air separation module contains thousands of fibers, and the fiber walls are permeable, so some gas types can go through the wall, but nitrogen is bigger, so it passes through and at the end of the fiber into what we call nitrogen enriched air. So that'll be the output. This then goes past an oxygen sensor to make sure the concentration is acceptable. So what we're looking for is something less than 12% O2. Ideally 9% O2 would be better. And then there'll be some kind of distribution system, which for a civil aviation aircraft would be tubes to each tank to ensure that all the tanks get inert air. Obviously it's more complicated for military because there'll be a lot more tanks to inert. The future of OB systems is changing slightly, and there's a way of using a catalytic converter to avoid using engine bleed air. So this is more suitable for helicopters or piston engine aircraft. This new system would use a blower to extract the ullage gas from the fuel tank, and then the gas is reacted in the catalytic converter, and then the gas is cooled and dried, and then return back to the fuel tanks. So this provides a continuous cycle rather than having to continuously extract engine bleed air. And I think that is the last slide. So thanks very much for listening. And if you have any questions, I'll just unshare my screen.
Well, thanks very much indeed, Manuel. That was very interesting. We do have a couple of questions for you. First question's about cavitation, and it's what kind of pressure drop from pumps can cause cavitation in aviation fuels, or where would you find that information?
All right. Typically, cavitation would occur if your engine interface pressure exceeded your pump capabilities, or if your fuel was vaporizing. So what we're trying to do is pressurize the fuel such that we don't exceed the vapor pressure of the fuel. And we also make sure that the engine demand isn't exceeding the boost pump capabilities. So if there was that kind of, well, it's going to be one of those questions where the answer depends on where you are. So if you're at higher altitudes, the vapor pressure of fuel is lower. So what you tend to find is that there will be an altitude limit for aircraft, which will be based upon where you can actually get to without vaporizing the fuel. About sea level, vapor pressure is not so much a problem.
All right, thanks very much, Manuel. Next question is about safety, and it's saying, what safety features are implemented during refueling to avoid damage to either aircraft?
In terms of air and refuel, there's mainly lots of training. Obviously, the interface between the two aircraft is designed to be strong enough to receive normal loads, and then a lot of training is in place to make sure the pilots don't exceed those loads. But as we've seen from the videos, pilots can get into situations where they do exceed or fail to hit the right spots, which can lead to accidents. So there was a recent accident last year where an F-35 collided with a C-130 tanker. So it can be a dangerous operation.
All right, thanks very much, Manuel. Next question is, would an output flow measurement on each tank be sufficient to measure how much fuel has been used by the aircraft?
It could be used, yeah. It's not tend to be something we do use. Flow sensors tend to be fairly inaccurate for low flows, and sometimes rates could be fairly low, but it's one option.
Okay, it's one option. Thank you, Manuel. Another question then, if you're okay with them, is how do you guarantee fuel supply to the boost pumps throughout the aerobatic G envelope?
That's a good question. So a lot of the time you don't. You size your engine feed system to have a certain duration, and typically the military specs allow for 30 seconds of inverted flight at dry power and 10 seconds afterburner.
Okay, thanks very much. The next one is pumping or sucking using self-priming pumps safer? Which is the safest?
typically we make sure that pumps are submerged in fuel. And we'll have sumps as well. So even when the tank is empty, there'll still be a lower sump for the pump itself. So I would say that pumps are always primed.
Okay, thank you. The next one is about, from past experience of accidents caused by fuel ignition, how has that influenced the design of aircraft fuel systems?
Well, there's a big push to make sure that ignitions and spark ignitions don't occur. So in civil aviation, there will be an aerobic system on pretty much every aircraft. On military aircraft, that's also increasing as well. So a lot of the new aircraft are looking at putting on aerobic systems.
All right, thanks, Manuel. And another question is, do you think that there will be a viable alternative fuel that could be used within the next 10 years, or perhaps even longer, which would dramatically reduce the environmental impact of passenger flight?
I think we're certainly trying to achieve that. As I said, it just depends on how we can actually grow the crops to create the fuel. That's going to be the big problem, I think. But I think the technology is there to produce the fuel. It's just the amount of land you need to actually create the amount of fuel you're going to need is significant.
Thanks very much. Manuel, can you foresee what the next big innovation might be in aircraft fuel systems?
Well, probably to get rid of them completely and have batteries.
Okay, and is it best to use positive displacement pumps or centrifugal pumps?
I would say for fuel systems, centrifugal pumps are better because they don't generate as much pressure.
All right, thank you. And do you foresee routine air-to-air refueling of unmanned systems in the future?
Yeah, I mean, they've already proven a UAV can refuel and a UAV tanker can provide fuel, so there's no reason why a UAV tanker and a UAV refueling receiver can't be up in the sky together.
All right, thank you very much. That's actually all we've got time for today. So thanks for answering all those questions, Manuel. I'm going to hand back to Thorai now.
Right. Hello again. What an absolutely splendid presentation it was, and especially the questions. First and foremost, I would very much like to thank Manuel for an extremely good and very educational presentation. Starting with the simple, using simple graphics, how starting with this fuel storage facility, the complexity builds up step by step. I thought that was beautifully explained. And by the time you've eventually sort of completed the diagram, it's such a mess. The mind boggles. So that was very, very useful. And the other thing is, of course, all the bewildering variety of interfaces that were discussed. So that was also very, very useful. You also went through all the mineral and the synthetic fuel grades, all the blending of the bewildering variety of fuels available. And it's just it's a bit amusing to find that the future aircraft will have increasing levels of cooking oil, as well as oil derived from sugarcane, fueling these wonderful aircraft. You also went through all the various tanks, especially elastomeric tanks, self-sealing tanks, removable tanks and external tanks, etc. One of the things I couldn't help getting a bit concerned was that the fuel pumps, which are immersed in the fuel itself, are run at a voltage of 270 volts. Normally should be a problem, but as the fuel tank empties and the fuel becomes sort of full of gases, etc., you just hope that the fuel suppression system or the nitrogen enrichment system is working properly. 270 volts and aviation fuel, that would, but I can understand the reasons for it. The other thing that was particularly important, particularly impressive, was how tight the lateral center of gravity control is. 5 to 10 centimeters, that's 4 inches maximum in old money. That is very, very tight control, especially when you start releasing stores, etc. And then, of course, you went on to the pressurization system to prevent boiling, but at the same time, you had to be able to vent into the tank during descent. And also, it'll be interesting to see why BEng, having developed the ultrasonic system to measure the fuel quantity, decided to go back to a capacitance-based system. But what was particularly nice, I think, was the way you calculate the fuel weight, how you compute the density of the fuel under those particular circumstances, and so on. I think the young engineers would have found that particularly fascinating. Then, of course, we went through all the fuel jettisoning system, and it also, another amusing item was that the F-35 Lightning also needs protection from lightning strikes. And of course, the usual ballistic protection system that would be needed in an aircraft of this type, a military aircraft. And finally, of course, you also talked a little bit about the pressure swing system as used on the C-17 and the V-22, etc., and the chemical reactions that take place in order to generate nitrogen-enriched air. It's always fascinating to me, and also the future, which uses a closed-loop system using based on the ullage gas, which means you will not need any bleed air from the engine. And finally, there were some very, very nice questions, starting with cavitation, etc. And it is very clear that your lecture has generated an awful lot of interest. So I would like to very much thank you for an absolutely splendid presentation and also a wonderful discussion at the end of the session. I would also like to take this opportunity, please, to thank a few others. First of all, I'd like to thank David Atkinson for presiding over the Q&A session, and also Emma Pateman at the Institution of Mechanical Engineers headquarters for keeping an eye on these matters, and also our chairman of the committee, that's the Institution of Mechanical Engineers Aerospace Northwest Committee, David Entwistle, who's unfortunately not to be able to be with us today, in addition to, of course, the secretary, Rebecca, and all others who made it all possible. So extremely well organized, and thank you very much indeed for a wonderful presentation. So I would like to take this opportunity to give an applause, please. And finally, just a quick reminder, this has been recorded, so the web links will be sent to all attendees at a future date. Thank you very much, and goodbye for now. Bye for now.